In the previous lecture, we have talked about the totally bounded set. So what is a totally bounded set? You want that A, which is a subset of a metric space, X, if you want to say that A is a totally bounded, if there exists or for given epsilon greater than 0, there exists a finite number of subsets A1, A2 up to An with a diameter is less than epsilon of X such that A will be covered by union of AI, where I running from 1 to n. That means A could be covered by finitely many subsets of X whose diameter is less than given epsilon. Then we can say that it is totally bounded. We have proved that totally bounded, so any set which is totally bounded implies the bounded. The converse of this result is not true. We have seen the example in L2 space, which is a square summable sequences. In that we have defined a set A, which is EI, for I belongs to N, where EI is the set or is the element which having the ith entry is 1, all other entries are 0. So this is an ith entry. And we have proved that this set A is not totally bounded, but it is a bounded into the L2 space. That we have proved in the previous lecture. Also, we have taken another example where if you can consider X with the discrete matrix, and if X is a infinite set, then this X is also not totally bounded. We also prove that A is totally bounded implies A closure is a totally bounded. That means a closure of a set is always a totally bounded. And we have discussed very important result which says that if A is totally bounded, if and only so A is totally bounded, that means if I call this is a statement 1, then 1 is if and only if every sequence in A has OC sequence. This is the another theorem which we have proved in the previous lecture, that the one part we have did, the converse part I have given you as a project to do it. So I think so we have done up to this much, and also we have proved that if A is a subset of R and A is totally bounded, then if and only if A is bounded. Ultimately, what I want to say is, if A is totally bounded, which is a subset of R, then A is a bounded. Or I can say that bounded and totally bounded are equivalent in R. So with this note or with this recall, we have to define a next very important concept which you will be very useful for your further study also. That is a compact set, compact matrix space. See, when you were in the further study, you have required some space, then all the times they are defined as a compact matrix space. a set which is a compact. The word itself suggests that means things which required is gives you lots of things, but still it is a compact. And the world is moving towards the compactness. For example, computer, if you can see that it's day by day it will become a compact. Okay, so that is kind of concept it is this, a compact matrix space. So a matrix space X comma D is said to be compact matrix space if X is totally bounded and complete. We have already defined what you mean by complete matrix space, and we already have defined what is a totally bounded. Complete matrix space means every Cauchy sequence is convergent in that space. That is called a complete matrix space. And in totally bounded set, we already defined earlier. So if a set which satisfying both this, that means if it is totally bounded plus completeness, then it is called compact matrix space. Now to prove this one, or to have the example of such matrix space, let us consider a closed interval 0, 1 with the usual metric on it. Then it will be a complete matrix space. So consider this example, that is, if I have X which is closed interval 0, 1 with usual metric. Then this X is a compact matrix space. Why? Because this closed interval 0, 1 itself is a closed set. Okay. And it is a subset of a complete matrix space. So we have one result we have learned, that if X is complete and A is a subset of X, then A is closed if and only if A is complete. So here this closed interval 0, 1 is a subset of R. And under R, this set A, X, is a closed set that we have closed interval 0, 1. So it will be complete space. And why it is a totally bounded? Because it is a bounded. Because we have just seen that, or we have talked about this, that if you have any subset which is a subset of a real line, then A is a bounded. If and only if A is totally bounded. This is the things which I am talking about. So that by that argument, this closed interval 0, 1 is totally bounded as well as it is complete. So that's why it is compact. So I can write this argument here. We note that this closed interval 0, 1 is totally bounded as it is bounded subset of R. Because it is a bounded subset of R, it is a totally bounded. And also closed interval 0, 1 is a complete as it is the closed subset of R. Therefore, this closed interval 0, 1 is complete. The second example, in that second example, I can say if I have defined this x with R with usual metric, then x is not compact. So here I should write down it is a compact, not complete. Therefore, x is compact. Here x is not compact. Why? Because it is not bounded. Okay, so we note that R is not bounded. Hence, it is not totally bounded. And therefore, R is not compact. So can you give me some examples which is not complete but it is totally bounded? So if I define a set which is X, which is open interval 0, 1 with usual metric. So here this space closed interval 0, 1 is not complete because it is not closed, as our argument that any space which is a subset of a complete metric space, then it gives you completeness if and only if it is a closed. This set is not closed because 0 is a limit point of this, which is not in this set. So we can say that here that X is not complete, as it is not closed subset of R. Therefore, X is not compact. So this will gives you idea that you can have what are the subsets of R which are compact. All the closed intervals, if you can consider any closed interval, is always a compact as a subset of R with the usual metric. And we have learned one things in the previous lecture, that a set A is totally bounded if and only if every sequence in that set in A has OC sequence, and A is complete, that will gives you every OC sequence is convergent. So with the help of this two result, can somebody from you state a next result regarding the compactness? Yes, can somebody define or can state the next result for compact set? See, A is compact means it is a totally bounded plus complete. That means this two statement has to be true. So what will be the result for compact metric space? X is compact metric space if and only if. Yes, from you, anybody?
Every sequence in A has Cauchy sequence.
Yeah, that is there. every sequence in A has a Cauchy sequence. That is there. That is gives you totally bounded, and completeness gives you Cauchy sequences convergent. So final statement is every sequence in X in that are taken X. That's why has convergent subsequence, because every Cauchy sequence has to be convergent. So it will gives you any sequence xn in X as convergent subsequence. So this is the statement. It's another definition of compact matrix. In some of the book, for example, a Munker's book, they have defined this is as a definition of a compact matrix space. They have defined a compact matrix space means that every sequence in X has convergent subsequence, and from this one can prove that A is totally bounded and A is complete. That is also one of the ways to define as a compact matrix space. If somebody wants that as a project, that they can do it. That any sequence which is this is actually known as a sequential compactness or sequential definition of a compactness. So you, with the help of this, you may prove that A is totally bounded, A is complete. If you assume this is as a definition and then prove that this concept. So let us give the proof of this. Let us assume that X is compact. So obviously we will use this two results which we have already stated here. That A is totally bounded implies this we have this, and A is complete, which is implies every Cauchy sequence has convergent subsequence. So sorry, every Cauchy sequence is convergent. So X is complete. And let us consider this Xn be a sequence in X. Since X is compact, it implies that X is totally bounded. Since X is totally bounded, as we have discussed that any sequence has convergent, any sequence has Cauchy sequence in it. That is the result which we have did. So we can say that Xn has Cauchy sequence Xnk in X. And since X is complete, because compactness implies the completeness and totally boundedness. So that's why X is complete, and this Xnk is a Cauchy sequence in it, and the definition of a complete space says that every Cauchy sequence is convergent, which will imply that Xnk and since X is complete and Xnk is Cauchy sequence, Xnk is convergent in X. So therefore we can say that the sequence, or I can say any sequence Xn has convergent subsequence Xnk in X. So which proves our objective that X is compact implies that every sequence has convergent subsequence. Now the converse part. So conversely, suppose that every sequence xn has convergent subsequence. Xn k. Let's say that is xn k is the subsequence of that. Now we need to prove that A is totally bounded and A is compact. Complete. So I will start with x and k is a convergent sequence. Will implies that x and k is Cauchy sequence. In X. So what I can say is every sequence xn has Cauchy sequence in X, Cauchy subsequence in X. Therefore, I can say any sequence xn, any sequence xn in X has Cauchy sequence xn k in X, which is exactly the statement which we have discussed, that A is totally bounded if and only if every sequence in A has Cauchy subsequence. So that will gives you that A is totally bounded. Cauchy subsequence. A is totally bounded. Not A, but X. X is totally bounded. Now we will show that X is complete. So it is enough to prove that every Cauchy sequence in X is convergent. So I will start with let xn is a Cauchy sequence in X. Then this Cauchy sequence has a convergent subsequence, because as per our assumption, every sequence has convergent subsequence. So this Cauchy sequence has convergent subsequence. So by our assumption, the sequence xn has convergent subsequence in X. So obviously this is a Cauchy sequence, and we have proved one result, that every Cauchy sequence has convergent subsequence, then it is complete. Okay? Or one can give the argument that if it is a subsequence, then it automatically converges to a same point if this sequence is there. That can be easily proved. If it is a Cauchy sequence and it is a convergent subsequence, if this Cauchy sequence has convergent subsequence, then it is complete. This result is also we have did in the previous lecture, of previous chapter actually. In the unit number 1, we have discussed this result, that any sequence which is Cauchy and has convergent subsequence, if and only if it is complete. So therefore, this X is complete, and therefore X is compact. Now the next result, can we have any relation with the compactness? That means if X is compact and X is closed, can we state some result like completeness? Under the complete metric space, any space which is a close, if and only if it is complete. That is the statement we have did. So is the similar kind of statement, can we make it for compact and closed? So this is the next result regarding the same argument. If A is a closed subset of compact metric space, X comma D, then prove that A is compact. That means a closed subset of a compact metric space is always compact. What about the converse? That means if A is compact, can we say it is a closed always? These are the results which we can establish. Okay, let us give the proof of first this one, and then we'll talk about the converse of this result. Now, what is our objective is to prove A is compact. So either you can prove that A is totally bounded plus complete, or you have another result which you can use that every sequence in A has convergent subsequence in A. So we shall show that any sequence xn in A has convergent subsequence in A. Let us consider, let xn be a sequence in A. I have to prove that this xn has convergent subsequence. But A is a subset of X which is given. So I can say therefore xn is a sequence in X also, because A is a subset of X. So as xn is a sequence in A, it is automatically a sequence in X. And since X is compact and xn is a sequence in X, so therefore this xn has a convergent subsequence. Which converging to a point X in X. I have to prove that this point it is in A. But then what will happen? This X is a limit point of A, because this xn is converging to X and xn is a sequence in X. So I can therefore this X is a limit point of A. But A is closed. A is a closed set and this limit point it is in X. So therefore X is in A. Therefore what I have proved here is xn which has convergent subsequence which converges to X, and that point X it is in A. So that means any sequence if I pick in A will have convergent subsequence. Therefore, every sequence xn in A as conversion subsequence in A, and therefore this A is compact. So which proves that if X is closed, sorry, X is compact and A is a subset of X, A is closed, sorry, A is compact, closed, yeah, A is closed implies A is compact. What about the converse part that we have discussed, that whether the converse of this result is true? The converse is true, but there is no requirement of that X is compact. That means A is compact, which automatically implies that A is closed. There is no requirement of any, this A should not require that it is a subset of a compact matrix space. Let us try to prove that also. So the next result, let A be a subset of a matrix space. I have taken a matrix space, not a compact matrix space. You can just see that X comma D is just a matrix space. And if A is compact, then prove that A is closed. So compact implies closed set. Let us try to prove this statement. Here I want to prove that A is compact, sorry, closed. So I have to prove that every limit point of this set A, which is in this set. So let us consider let X comma this X which is in X be a limit point, any limit point of A. Since it is a limit point, therefore there exists a sequence xn in A such that xn is converged to X as n tends to infinity. What to show? We have to prove that we have to show that X belongs to A. That is our objective. A sequence which is in A and A is compact, which is given. So since xn is a sequence in A and A is compact, will implies that xn has a convergence subsequence. Not therefore, I should not write therefore here. xn has sequence, sorry, convergence subsequence. Subsequence in A. This is very important. The subsequence is there, but that subsequence has to be in A. And since this subsequence which is converged to A and xn is itself a convergence sequence, so subsequence is also converged to a same point. If a sequence xn is convergent and its subsequence is also convergent, then a sequence automatically converges to a same point. Okay. So we can say a sequence, we note that sequence and its subsequence converge to same point x, and x is automatically, this subsequence is converging A, so that means this x is belongs to A, and therefore A is closed. So ultimately what we have did is A is compact implies A is closed. But the converse of this result is not true. The example is, you can consider this 0 to infinity. This set is a closed set, but it is not compact. It is a closed, but not compact. Why? Because it is not bounded. It is a subset of R with the usual metric. So the converse of this result is not true. If you want the converse is true, then you require your X will be a compact, and A is a subset of that. So in that sense, this result will be true in that matrix space. So we can have another result which we can just see by seeing that we can say that any compact matrix space is closed and bounded. So can somebody give me proof of this in your words? A is compact will implies that it is a closed plus bounded. See, we already proved that A is compact implies A is closed. So the closeness is already proving previous theorem. Why it is bounded? Because A is totally bounded, and totally bounded implies boundedness. So I am giving you this as a homework. You can see this very easily. Closeness will given by previous result, and the boundedness will given by totally bounded. Because it is a totally bounded implies that it is a bounded. The question is whether the converse of this result is true. That means closed plus bounded, can we say it is a compact? The answer is no. We have example L2. In that A we have discussed what is A is set of all EI where I belongs to N. This is not totally bounded set. Sorry. Okay, this will not work because this is bounded. I need to have an example which is closed plus bounded will be not compact. Yeah, so I can give this example. Closed plus bounded. So in real life, if you can try to find out this example, then you cannot able to. So you have to look at for the another space. Yeah, so this is a bounded set, but it is not totally bounded. This will work, definitely work. Yeah, it is not totally bounded, so that's why it is not compact. Okay, but it is a closed set that you can prove easily, and it is a bounded also. That also one can prove that. So what will when the question is when the converse is true? The converse is true when you have a real line. That means we have a next result with that. It says that any subset E of R with absolute metric, value metric. Absolute value metric means d of xy is equal to mode of x minus y for every x when y belongs to R or E. This is absolute value metric. Then prove that E is compact if and only if E is closed and bounded. For the proof, we already discussed that A is compact. E is compact, then it is closed plus bounded. It is for any space, it is true. But let us try to give the proof for that also. Suppose that E is compact. If it is a compact, then this will imply that E is totally bounded. Which will imply that E is bounded. Okay, so that is the first one is bounded is done. Now we have to prove that is a closed. Since E is compact, E is complete. Now E is complete and E is a subset of R and R is also complete. So as we have talked that any subset of a complete matrix space, it is equivalent that completeness plus closeness. So therefore E is closed. So that means any compact set which is bounded plus closed. Converse. That is this side. That means E is closed plus bounded. Can we say it is a compact? So since E is a bounded, we can say that there exists a real number A and B such that E is a subset of AB. Since it is a bounded, there exists some real number AB with A is less than B such that E is a subset of this. But this is a compact. Closed interval AB is a compact matrix space that we have already did argument. And E is a closed subset of a compact matrix space. So we have proved that as a result that we have discussed here that any subset which is a compact, this is the result that any closed subset of a compact matrix space is a compact. So we use that result here that this since closed interval AB is a compact and E is a closed subset of closed interval AB, therefore E is compact. So which proves that E is compact if and only if E is a closed and bounded. This is very important result in the NET for the NET examination or any competitive examination you are preparing for. This concept is very important. There are many questions based on this things. So the next remark we should write here is whether the converse of this result is true or not. That means if E is a subset of R, if I drop this condition, can we say that it is there? So the answer is already given. I have already given that answer that if you can say L2 space, which is a square summable sequence, and if you define this A, which is each of this AI, where I is running from or belongs to N. So can you say that this A is compact? No, you cannot say. but this A is a closed and bounded, but it is not compact. So if you drop this as a subset of real line, this is not okay. If you have any question, you can ask.